Welcome to this webinar on GWTC 2.1, the deep extended catalog of compact binary coalescences observed by LIGO and Virgo during the first half of the third observing run. Next slide. I'm Benoît Moore, and I will be the moderator for this webinar. I'm pleased to introduce today's speakers, who are all directly involved in the production of the GWTC 2.1 paper. We will have Antonios Kontos, then Surabhi Sachdev, who lead the paper writing team, Anaria Ray, Daniel Williams, Carl Eister, and finally Michela Mappelli. Next slide. During the webinar, you can type your question in the Q&A box. Then they will be answered either online or at the end of the webinar. To help us in this task, we have another set of experts with us, with Derek Davis, Thomas Dent, Veronica Wheeler, Imre Bartos, Anjali Yelikar, and Kent Blackburn. They were also all deeply involved in the preparation of the GWTC 2.1 catalog. Before moving on, I would like to remind that producing such a paper requires first to get amazing detectors, the LIGO and Virgo instruments. We are all grateful to the so many scientists, technicians, engineers, and other staff from the labs that dedicate their time to the design, construction, and operation of these instruments. Next slide. As you may know, a year ago, we already published GWTC2, the first catalog of sources for the O3A observing run. Well, you may ask, what's new with this 2.1 version? First, this is the analysis of the best O3A data set release, and Antonios is going to describe this part. Then we wanted to find more events by improving the searches. Surabhi will tell us the change made, the analysis and the results obtained, highlighting the 8 new candidates events. Anaria is going to tell what we learned from the source population rate. Then we wanted to have source parameters computed in a more uniform and up-to-date way. Daniel and Carl will tell us more on this. And as you will see, the 8 new events are quite interesting. Michela will tell us what we learned with them before the data release, and finally moving to the Q&A session. And now let me hand over to Antonios.
Hello, everyone. Since this paper covers the same observing period as GWTC2, there is really nothing new to add on the instruments. However, it is worth reminding ourselves the incredible leap in sensitivity between the second observing run and the third observing run, between O2 and O3. Through a series of instrumental upgrades, such as higher power and more stable lasers, quantum squeezing, scattering light mitigation, optic and suspension upgrades, improvement in controls, and others, there has been a big increase in sensitivity. This can be measured through the binary neutron star range, or the so-called BNS range. The BNS range is the distance at which a single detector could observe the coalescence of a pair of 1.4 solar mass neutron stars with a signal-to-noise ratio of 8. As we can see here, the increase in sensitivity for Virgo was 73%, for Hanford 64%, and for Livingston 53%. Considering now that the detection rate depends on the volume, you can raise these improvements to the third power, and you will see the improvement in the detection rate. Next slide, please. On the data side, there have been some changes relative to the data in GWTC2. The bottom line is that all the analysis in this paper use the best available calibrated and clean data. What I mean by that is the following. What gravitational wave detectors measure are optical power fluctuations in the photodetectors caused by the motion of the mirrors. The process of translating volts to strain is called calibration. And calibration comes, of course, with uncertainty, which is complex valued and frequency dependent. All analysis in GWTC2 use the best available data with a very well understood calibration uncertainty. Next slide, please. A significant difference in the data is the additional subtraction of 60 Hertz power line noise using a novel technique for cleaning non-stationary noise. This figure shows the data before and after the subtraction. While the range of frequencies seems narrow, around 60 Hertz, the impact of this additional subtraction in the PNS range is significant, being as high as 0.9 megaparsecs for the Hanford detector. Finally, we performed quality checks similar to the ones described in GWTC2. It is worth mentioning that we identified no glitches around the new events presented in this paper. Now I hand it over to Surabhi.
Thank you, Antonio. So I'll be discussing how we identified candidates for our catalog. We used 3 match filtering pipelines for compact binary coalescences, GST-LAL, MBTA, and PyCBC. PyCBC was ran in 2 configurations, PyCBC and PyCBC-BBH, making 4 total analyses. All the pipelines use data from all 3 detectors. GST-LAL also reports events that had significant SNR in just 1 detector. We're reporting results from MBTA for the first time in an offline catalog. We provide both the false alarm rate and the probability of astrophysical origin for all our candidates. While GWTC2 used a false alarm rate threshold of 2 per year, which resulted in 39 candidates, here we use a false alarm rate threshold of 2 per day. And we have 1,201 candidates that pass this false alarm rate threshold. While most of these candidates are expected to be from noise, cross-correlation studies of subthreshold candidates from this catalog with other astrophysical surveys could lead to a multi-messenger discovery. We also provide, in addition, source properties of a subset of these candidates, which are high significance that have a p-astro threshold greater than 0.5. This leads to 8 new candidates in comparison to GWTC2. This catalog is a catalog of compact binary coalescences, which include binary black holes, binary neutron stars, and neutron star black hole sources. We use modeled searches to detect these sources. The model searches perform match filtering of the data with model templates. These model templates rely on intrinsic parameter of the sources, which are the 2 masses and the 2 spins of the objects in the compact binary. In addition, the searches make the simplifying assumption that the spins of the 2 components are aligned with the total orbital angular momentum of the system. In addition, they also consider just the most dominant 2-2 mode of the waveform. Here, I'm going to tell you about the parameter search that was searched over by the different match filtering pipelines. GST-LAL looked for compact binaries with masses between 1 and 400 solar masses, going up to a total of 758 solar masses. The template bank included 1.7 million templates. GST-LAL uses IDQ, which is a statistical framework to infer periods of bad data quality using auxiliary witness channels. Previously in GWTC2, IDQ was applied to all candidates that were found in just a single detector. Now in GWTC2.1, we use IDQ in all candidates, whether they were found in a single detector or 2 detectors or 3 detectors. The template bank for MBTA included masses between 1 and 195 solar masses, going up to a total of 200 solar masses. It had about 700,000 templates. This is the first time that MBTA was used in a catalog. It wasn't included in GWTC2. For PyCBC, we looked over compact binaries with a total mass of between 2 and 500 solar masses. The template bank had about 400,000 templates. PyCBC-BBH uses a subset of this template bank, which is targeted towards binary black holes with a mass ratio between 1 and 3 and component mass between 5 and 350 solar masses. Both PyCBC and PyCBC BBH analyze data from just Hanford and Livingston in GWTC2, but in GWTC 2.1, they're now analyzing data from all the 3 detectors. False alarm rate is calculated using only the background distribution of the ranking statistic that is used by the search, while astrophysical probability, Pastro, is calculated using both the foreground and the background distributions of the ranking statistic. All searches are going to estimate membership probabilities for the 3 source classes that we consider: binary neutron star BNS, neutron star black hole NSBH, and binary black hole BBH. Class membership is based on component masses only. It doesn't necessarily imply that the components are actually a neutron star or a black hole. We are unable to measure any matter effects at this time. Since the foreground rate of binary black holes is much higher compared to that of the binary neutron stars and neutron star black hole binaries, the astrophysical probability inferred at a fixed false alarm rate is greater for binary black hole than for binary neutron star and neutron star black holes. So here's the distribution of the source probabilities for all the candidates in GWTC 2.1. The sum of Pastro represents the Poisson rate of sources that pass the 2 per day threshold in each class. So for example, the rate of binary black holes in our catalog for GSC LAL is 34.5, for MBTA is 29.6, for PyCBC is 24.9, and for PyCBC BBH is 44.5. Again, just a reminder that the source classes membership only depend on the component masses. PyCBC and GST LAL consider a boundary of 3 solar mass between a neutron star and a black hole, while MBTA assumed a mass gap of 2.5 to 5 solar masses between neutron stars and black holes. These are the subset of events found in our catalog that have the Pastro greater than 0.5. There are 44 total such events that were found with Pastro greater than 0.5 in any of the analyses. We find 8 new events compared to GWTC2, while 3 events from GWTC2 now have a Pastro smaller than 0.5 and don't make it to this subset of our catalog. We have 2 events that have either the PBNS or PNSBH greater than 0.5, GW190425 and GW190814. All other candidates, according to our search analyses, fall in the BBH source class membership. We have 8 events with PBNS or PNSBH greater than 1%. Although GW190917 _11 4630 is assigned the BBH classification by the search pipeline, we will see that the detailed parameter estimation results find its masses to be consistent also with neutron star black hole. Here are the 3 candidates that were included in GWTC2 but did not pass a Pastro threshold of 0.5. GW190424 was found by GST LAL as a single detector trigger in LIGO Livingston. Data surrounding the event recorded glitching from a camera shutter, and IDQ, the statistical framework that GST LAL uses to identify bad data quality, times down rank this event, both in GWTC2 and GWTC 2.1. However, since in GWTC2, IDQ was only applied to candidates occurring in single detectors, we needed to retune the singles penalty that are applied to candidates that are found in single detectors only, which caused this event to be downranked and fall below the Pastro threshold. GW190426, this event was recovered with a false alarm rate of about 1 per year. This is similar to the false alarm rate that was calculated for the GWTC2 search as well. However, since the masses of this event are NSBH-like, the Pastro at this far threshold is below 0.5. And the last one is GW190909, which is now recovered with a lower SNR in Hanford with the final data and does not pass the Pastro threshold anymore. Now I'll hand over to Anarya.
Hello, everyone. As Binoy mentioned, I'll be talking about the updates to the estimates of sensitivity, search sensitivity, and astrophysical merger rates as reported in the GWTC2.1 and inferred from O3A data. So we infer search sensitivity by simulating signals and injecting them into the data, and then we calculate the fraction of the injections recovered, whereby recovered I mean detected given a threshold. And from that fraction of injections that were recovered, we estimate the volume time sensitivity of the searches by multiplying the astrophysical co-moving volume V in which the sources were injected with the fraction of recovered injections. And then we just multiply the search times to get the space-time volume sensitivity. And the injections used in GWTC 2.1 are different from GWTC 2.2. The most striking difference is that now we have injections for BNS and NSPH. And also we can, it's worthy to note that we can rescale the volume time sensitivity to any other astrophysical population than the one from which the injections were drawn. Okay, so next slide, please. We compute the merger rates from the sensitivity and the number of astrophysical detections. So first we rescale our simulated sources to the astrophysical distribution for which we want to infer the merger rate. And then we calculate the merger rate as the ratio of the number of astrophysical distributions to that of the volume time sensitivity. And to compute the number of astrophysical detections, we include triggers up to a very high far threshold, and we compute rates that are fully consistent with the rates inferred by the analysis that include only high significant triggers. For example, for the binary black hole merger rate for the power law plus peak population model, we find a merger rate of 25 gigaparsec cube, inverse gigaparsec cube year for GST-LAL, 26 for PyCBC BBH, and 25.6 for MBTA. And also we compute a merger rate for BNS for a population that is distributed uniformly in component masses. And we find a merger rate of 286 gigaparsec, but 286 per gigaparsec cube per year. For GST-LAL, we only report the GST-LAL rate for BNS because it's more accurate, since the other pipelines exclude triggers that were detected by a single detector. And this BNS rate is more constrained from the one in GWTC2, but it's also fully consistent. And now I hand over the mic to the next speaker.
Thank you. So after having found the set of detections, we want to estimate their astrophysical properties or their source properties. And this is represented in terms of several joint probability distributions shown here in the form of Bayes' theorem, where on the left you have a probability over the source parameters themselves, where the parameters we're interested in are primarily the mass of each compact object, so each black hole or neutron star, and also the three-dimensional representation of the spin of those objects as well. And then we also, of course, care about the location of the universe, so its position in the sky and the distance to the source, as well as the orientation of the binary in the universe. Our inference of these parameters depend very strongly on the data, as Antonius described earlier. And in this analysis, we're using the recorded strain from all the detectors operating at the time of the detection. And as an upgrade to previous studies, here we account for the uncertainties in the calibration of the data in all of our analyses. On the right side of this equation, we have the likelihood, which tells you how likely a certain set of parameters are to actually describe the data you're seeing. And this is done as a comparison between the type of pre-calculated models that Sarabi mentioned earlier and the data. And then we assume that the residuals between the model and the data are distributed like a normal distribution. And finally, we have a set of prior probability distributions, which tell us how well we think certain parameters and certain parameter combinations are to exist in the universe as a whole. And these are defined to be uniform in the masses as observed here on Earth, and then also uniform in the dimensionless spin magnitude of the compact objects, isotropic in the spin orientation, and then we're finally using a distance prior that is proportional to the uniform density in the co-moving frame, which roughly means that we believe that every single piece of volume in the universe is as likely to contain a source as any other. And then I'll briefly hand over to Daniel.
Thanks very much, Carl. So the preparation of GWTC 2.1 in parallel with the analysis of O3b for GWTC3 posed a new challenge in terms of logistics in making sure that all of the analyses could run together and in a timely fashion. And in addition to the 8 new events which we present in GWTC 2.1, we have conducted reanalysis of all of the binary black hole signals from O1 and O2 and O3a. The analysis of these papers is considerably more complicated than it's been in previous catalogues, and we now use multiple different pipelines, which each have their own unique configuration requirements. So to organize this process, we developed Asimov, which is a Python package which interfaces both with our computing infrastructure, which runs principally on HT Condor to schedule jobs, and with our various pipelines and data sources to make sure that the correct interferometer data is gathered, along with information which comes from initial human-run parameter estimation studies and information about the data quality of the individual segments which we're analyzing. And these are used by Asimov to construct configurations for each pipeline, which are then used to produce the final analysis. In addition, it allows us to automate the calculation of on-source noise PSDs using the Bayes-Wave pipeline and conducting the parameter estimation using Rift, Bilby, and LAL inference as the primary pipelines which we use to produce posterior samples. Next slide, please. So once we have the raw posterior samples produced by these pipelines, they also need to undergo various stages of post-processing to produce the final results. And Asimov robotically monitors the progress of all of the analyses and all of the post-processing jobs to allow the analysis to be completed with a fraction of the human intervention which would have been required using the approach which we had for previous catalogues. So we managed to reduce the total person power requirement from several dozen people running analyses to a small team of people to both monitor the operation of the robotified process and some experts to pick up any unusual situations which we encountered during the analysis. So thanks, I'll hand back to Carl.
Thank you. So to continue on from the previous discussion, we, as also mentioned by Sarabi, we as part of this analysis being using a set of waveform models to describe the signals we believe that we should see. Well, we now use a varied set of such models in the detailed source properties analysis as well. So all the models we're using for this study include effects on the orbital precession that are induced by the black hole spin, and also for all the compact object spin, and for binding black holes, we include models that contain both the dominant and subdominant multiple moments of the gravitational wave radiation. An example of this is shown here on the right, where much of previous analyses, including the gravitational wave searches in this study, are using only the dominant gravitational mode, labeled here in orange as LM equals 22. Whereas a complete gravitational wave signal, shown here in gray, will also include contributions from many other sets of modes. And while the difference between the orange and the gray lines for this specific sample is relatively small, the difference is substantial enough for us to actually observe it. So the inclusion of more gravitational wave modes can allow us to put both generally tighter constraints on the inferred source properties, but also to potentially break certain parameter correlations that we would be interested in not seeing anymore. Next slide, please. So today I'll focus primarily on the properties of the 8 new events presented in this catalog. But the paper itself will also include results for all the other observed binaries from both the first, second, and the first half of the third observing run from LIGO and Virgo. So shown here are representations of these source property probabilities, where going from left to right, we have the primary mass and then the secondary mass. The third column shows you the mass ratio, so the ratio between between the secondary and primary mass. The fourth column shows you what we call the effective spin. So this is the spin or rotation of the two compact objects projected onto the orbital angular momentum, and then also accounting for the different mass between the two objects. And finally, we're showing the luminosity distance for each source. Next slide, please. So here I'm showing a 2-dimensional plot with the total mass on the x-axis and the mass ratio for all the 8 binaries. The general trend that we see for these 8 new binaries is that the masses are comparable, or even higher than the binaries that have been observed in the past. And this includes the most massive binary black hole observed with gravitational waves overall, which is GW190426, with a total mass of around 185 solar masses. 2 of the binaries found in this category of 8 have median mass ratios such that we believe that the larger object is at least 4 times as massive as the smallest one. And these are the 19403 binary and the 190917. I would also want to highlight the dashed lines shown in this plot, which represents the rough boundaries where we believe an object is either a black hole or a neutron star, which is at the 3 solar mass line that was mentioned earlier. And specifically, you'll notice that effectively or 7 of the 8 binaries have effectively all of their probability, all of their contours so above or to the right of the M2 equals 3 dashed line, which means that we believe that they are binary black holes in this case. And only one binary, 19917, has the majority of supports below this line, which then means that we would classify it primarily as a neutron star black hole binary. Next slide, please. We're also interested in the spin or the effects of the spin of these binaries. And what's shown here is another 2-dimensional representation between the effective spin that I mentioned earlier on the y-axis and the so-called chirp mass on the x-axis, where the chirp mass is this certain combination of the primary and secondary mass shown here in the equation on the right. The takeaway from this plot is that most of the binaries that we have observed in this set are very much consistent with chi-effective of 0, so showing no strong observable spin effects. But if there is a general trend, we seem to prefer slightly positive chi-effective values rather than negative one, which is in agreement with previous observations as well. And there are only two binaries, 190403 and 19805, which recover definitely non-zero chi-effective, again, both preferring positive chi-effectives, where 19403 is the more interesting one, which in its being the binary so far that we have observed with the highest spin magnitude and also the highest or near extremal values for chi-effective. Next slide, please. So we can also represent the spin parameters. So in a different form, and shown here is the representation of the magnitude as a radial gradient, and also the tilt of the spin. So the angle between the orbital angular momentum and the spin vector for each object, with the primary objects parameters shown on the left and the secondary objects on the right in each spin disk. Whereas for the secondary objects, the semicircles are largely uniform in color, which means that we can't say very much about the specific combinations that, well, we don't have any specific preference for any specific parameter combinations. Whereas as shown on the left-hand sides of the plots going forward the slide, for certain mass combinations, we can actually put tighter constraints on the primary object's spin, with again the highlight being the strong preference for nearly aligned and near extremal spins for 19403. Next slide, please. And I want to finish with a short discussion about the localization capabilities for these 8 new events. They are all recovered with relatively modest signal-to-noise ratios, which unfortunately translates to a comparatively poor scale localization of these binaries compared to previous ones, with the best localized binary shown here in this plot of the sky, with a localization much, or at least greater than 1,000 square degrees from the sky. One benefit, though, of the low SNRs is that usually correlates to large distance or large infinite distances, which is true in that we're now probing a very high redshift binary population, with again 19403 being the most extreme one, recovered at the redshift generally much higher than a redshift of 1. And with that, I'll hand over to Michaela.
Thank you, Carl. So now let's talk about the astrophysical implications of our new events, assuming that they are of astrophysical origin. And first, I will briefly summarize the main features of the astrophysics scenarios, starting from the isolated formation channel. In this channel, a binary compact object forms from the evolution of a massive binary star, either via common envelope or an episode of stable mass transfer, or via chemically homogeneous evolution. And we expect that the binary compact object will have preferentially equal mass, and that the spins will be nearly aligned or preferentially aligned with the orbital angular momentum of the binary system. In contrast, in the dynamical formation, the two compact objects pair up dynamically in an extreme environment like a dense stellar clusters or the gaseous disk surrounding an active galactic nucleus, an AGN disk. Black holes are particularly efficient in acquiring companions dynamically because they are more massive than neutron stars and other star objects. And dynamically assembled systems are expected to have a higher mass than the isolated ones. And lower mass ratios are also more likely. And we expect that the spins are isotropically oriented. Next slide, please. The formation scenario has an impact on the existence of mass gaps in spectrum of compact objects, especially the instability mass gap. When a star is very massive and metal poor, it is expected to undergo an instability at the end of carbon burning, which is called pair instability because it is triggered by an efficient formation of electron and positron pairs in the stellar core. And this instability is expected to open a gap in the mass function of black holes between approximately 65 and 120 solar mass. But the boundaries of the gap are still affected by large theoretical uncertainties. On top of that, the dynamical formation scenario can partially or completely fill the pair instability mass gap because of the hierarchical merger of smaller black holes in denser stellar clusters or AGN disks, and because of exotic stellar collision in stellar clusters. Next slide, please. So what can we learn about these astrophysical scenarios from our new events? First of all, we have a new intermediate mass black hole candidate with a mass above 100 solar masses at 90% credible interval. This is the remnant, the merger product of 1904-26_190642. And this brings to 3 the number of intermediate mass black hole candidates we observed with gravitational waves. They are 1905-21, 1904-26 that are from the first part of the third observing run, and then 2002-20, which is from the second part of the third observing run. And you will hear more about this event in the next webinars of the LIGO, Virgo, and Kagra collaboration, focusing on the GWTC catalog. Furthermore, we have 3 new black hole candidates in the pair instability mass gap, or just above it. These are the primary component of 1904-03. And both the primary and the secondary of 1904-26. Actually, the primary mass of 1904-26 has a probability, a non-zero probability of being above 120 solar masses, which means that this black hole could be above the pair instability mass gap rather than inside the mass gap. And to explain these new massive black hole candidates, we can invoke the same scenarios that we studied for 1905-21, which are the hierarchical merger of smaller black holes in stellar clusters and AGN disks, or star-star collisions in stellar clusters, or extreme episodes of gas accretion, or they could be primordial black holes from the very early universe. And we must not forget that the boundaries of the pair instability mass gap are uncertain, so we cannot rule out the isolated formation scenario. Next slide, please. As we have seen, the primary component of 1903 is possibly in the pair instability mass gap, but this event has other peculiar signatures, as Carl just discussed. It is a relatively low mass ratio system, which is more common for dynamical systems than for isolated ones, especially from the chemically homogeneous evolution. And it has a positive effective spin and a large spin of the primary component. Larger spins are typical of second-generation black holes. But here we have a possible second-generation black hole with a spin that is nearly aligned with the orbital momentum of the binary system. Alternatively, this black hole may have been spun up by tides or accretion or chemically homogeneous evolution. And now let me mention two other events, 1907-25 and 1917. The secondary component of 1907-25 has non-zero probability of lying in the lower mass gap between neutron stars and black holes. This mass gap is claimed based on the dearth of neutron stars and black holes with mass between about 2 and 5 solar masses, according to observations of nearby X-ray binaries. And finally, 1909-17, as component mass is consistent with a neutron star black hole system, like, for example, 2001-15, which belongs to the second part of the third observing run. And I'm done. Thank you. And I hand it over to Surabhi.
Thanks, Michaela. So we also made available a lot of data products associated with this paper. First of all, the full stream data of O3A, but also O3B is available via GWASC. The candidate data release is available via Zenodo. This includes the 1201 events that pass the 2 per day false alarm rate threshold, and also the corresponding sky maps, which can be useful for cross-correlation studies. In addition, we provide a Python notebook for instructions on how to read the data. We released the posterior samples for the 8 new events that we detected compared to GWTC2. We will also update it to include the events that were previously found in GWTC1 and GWTC2. That work is currently ongoing, and we include a Python notebook here as well for instructions on how to read samples. Finally, we also provide data release associated with calculation of the search sensitivity of the various compact binary coalescence pipelines that we used in our analysis. These are also available via Zenodo, and we include a README that details the data structure of the files that are provided. Now, these links maybe are going to be forgotten, but I think you can Google GWTC2.1 Zenodo to get to these various links. Lastly, I'll hand over to Benoit for some concluding remarks.
Thank you, Surabhi. So before closing this presentation, let me advertise a set of webinars associated to the very recent release of the O3B data, the corresponding catalog and associated papers. The first one will be on December 6th for the GWTC3 catalog. It will be the opportunity for you to ask questions on this new data and papers. Another piece of information is that we recently updated our planning. We have now a date for the start of the O4 run, mid-December of next year. The expected detector horizon improvement is in the 30 to 40% range, meaning a much larger number of detection and hopefully new exciting finding. I will stop here. Thank you for your attention. And now it's the time for Q&A session. So if you have additional questions, please type the question in the Q&A boxes. Before going to the maybe unresolved question, let me ask again, there were a couple of puzzling questions for us from Young Cow. If you can type again your question with a bit more explanation of what you are looking for, that could be helpful. I would like also to add some information to the question on the supernovae template. that were asked if we were including them. And I would like to remind that for the 2.1 catalog, there were no searches for burst, given the result of the first search that was carried on with GWTC2. And given the fact also that we wanted to have a threshold on Pastro, and computing the Pastro on N-model sources is quite a challenge. So the sources that were searched for this catalog were all CBC sources. So let me see if you have open questions. Or do we have one of the panelists that want to expand one of the answers that has been already given?
I can expand on one question from Hurisiyapur about, so the original question was if for the neutron star black hole candidates, we had checked any EM data to see if there was any transient or the EM transients that we could connect with our gravitation wave signal. So my original answer, to repeat it here, was that the sky localization for that for the NSBH candidates, which is 19 and 917, is unfortunately not great, as I mentioned in the talk. So it's consistent with coming from more than 2,000 square degrees in the sky, and additionally, it's recovered with at a distance of more than 700 megaparsecs, which would be outside of effectively every outside of the detection capabilities of effectively every EM telescope that's observing or that's online now. And to make things even more difficult for the specific binary, so based on the mostly on the mass ratio that we infer, which is fairly uneven, we would not necessarily believe there to be any matter from the neutron star left over from after being swallowed by the black hole to generate any electromagnetic signal to start with. So unfortunately for this binary, it looks bleak, but we're hopeful for more and clearer detections in the next observing run.
Okay, thank you, Carl. Thank you, Yang, for expanding a bit your questions. I don't know if is it Derek or Antonios want to try to answer a bit about, well, is that about the detector noise? Or, yeah. Okay, let's maybe postpone on that question about seismology approaches. What about the eccentric BBH? Tom, you want to go ahead with that question?
Yeah, thanks. So I might want to change the background. Well, okay.
Never mind about the background.
Sorry, okay. For some reason I've got a blurred background, which is not great, because I don't know why. Okay. Sorry about that. So, okay, eccentric binaries are very interesting possible sources. They could, if we find them, tell us a lot about how these binary black holes are formed. So in particular, if we see things with relatively high eccentricity, then this would indicate that the binaries were formed in a very dense environment with lots of black holes swirling around each other, which could be close to a galactic center. Now there's, we have a very big technical issue with doing such searches, let's say, with the existing technology, which is that the waveforms for eccentric binaries are a lot. So we don't, let's say, have a full, fully optimized answer to how we would search for eccentric binaries. So, well, that doesn't mean we ignore them completely. We do a, let's say, partly unmodeled search. So we employ existing searches for, let's say, not completely templated, not completely specified bursts of GW, and we see how, we try to employ these to look for possible eccentric binary mergers. So, I think Imre is also concerned with this sort of searches. So maybe we'll find something, and also people are looking at ways of seeing signatures of small amount of eccentricity in the events we've already discovered. So I guess watch this space.
Thank you, Tom. Let me answer quickly to one of the questions about the rate of event per day that is expected for O4. There with a 30 to 40% increase in range, we expect to see a volume that is a factor 3, maybe a bit more, maybe a bit less. And given the fact that we add 80 events for O3, that gives you a rate of, several per week. So is it going to be one every 2 days or so, or a bit more? We will see, but that's the order of magnitude. Do we have one of the panelists that wants to talk about the, well, you have the question about the low masses BBH that seems to be a multiple of 7 solar masses. I don't know if is a car or you want to take that? Or Nicola maybe in better position.
I'm happy to hand over to Michele.
This question is gone. Oh, move to another. Well, it got an answer right.
No, I can get it. You mean, sorry, I was typing another answer. You mean the one to Juan Francisco Gonzalez about the spinning stability mass gap? Which question were you?
I was talking about the one with the multiple of 7 solar masses.
Yeah, that was exactly what I was typing. Okay. So I can briefly summarize what I just typed. No, it's really interesting. Actually, I don't think I can call them patterns with specific multiples, but for sure, there are features in the mass function of primary components. If we look at the distribution of primary components and the reconstruction of the mass function of primary components after you remove, let's say, the biases. But these features are not unique of the hierarchical merger scenario. They could also originate from binary evolution. So there is some kind of degeneracy. And one good thing of the hierarchical channel is that it also predicts relatively high spins, so between 0.6 and 0.9, roughly speaking. So if you find massive events and also high spin, that starts to be a good argument for not a smoking gun maybe, but a good argument for hierarchical mergers. But the features in the mass function are not enough. They are interesting, but they are not enough.
Yeah, Tom, do you want to
add? Yes. So, and Michele has give us a very nice overview of the possible astrophysics of if there were some kind of curious features in the mass distribution. We also have to be careful whether such apparent clusters of masses around particular values could be just random, could be just something that your eye is tricking you into believing that they're there, looking at new actual physical, astrophysical features of the distribution. So one of the upcoming webinars, I think maybe in the first or second week of December, will be about the population analysis of, well, not just binary black holes, but all of our binary merger candidates through O3. And that's going to give you a lot more in terms of what we believe about the structure of the masses and, well, what we currently know and what we believe about which of these features is real or which of them are possibly just random fluctuations.
Thank you, Tom. We are almost at the top of the hour. So I propose that Carl answer to the last open question before closing.
Yeah, so this is a question from Francisco Gonzalez. So with respect to the parent stability gap, what are the most significant sources of uncertainty in the sample of this release? So there are several different answers to this. Part of which is the same answer that Tom just mentioned, in that when analyzing all the binary black holes together as a population, we can put tighter constraints on whether we believe, well, what properties we believe a potential parent stability gap to have. Then there are the second part of this answer is also related to what Michele mentioned in the talk about the specific astrophysics that go into to actually creating the theoretical possibility or likelihood of the gap as a whole. And then finally, from the side of the analysis, there are some minor discrepancies when we analyze these high mass events with different waveform models that we see. But those differences are fairly small and not dominating over anything else, fortunately. So from the results shown in this paper, the most uncertain thing is connected to the low signal to noise ratio of the high mass events themselves. So the fact that the signal aren't super loud to begin with. So there's inherently going to be a larger uncertainty in anything we try to recover.
Thank you, Carl. Thank you all for joining today and listening to this webinar. We hope to see many of you for our next webinar that will be on December 6th for the GWTC3 catalog. Bye, everyone.